So in today's workshop, I will first start with just a brief overview of what Webnozzles is, and it is very similar to the talk I gave on Friday. I will browse through it a bit, so if you've seen the talk already, then you should know already most of it, but might still be interesting. If you do have any questions, feel free to just interrupt me anytime in between, and we can make this a bit of a conversation. After that first bit of presentation, I'll go and jump into some code. So I've prepared a Jupyter notebook that I'll also share the link to, where you can follow along. And we're going to have 4 different examples of what we can go through. And again, there, if you have anything that you're particularly interested in about, then we can also do that. And this is I'm happy to make this as useful as possible for everybody who joined today. So let me know really what will be interesting for you. But I think just to get things off the ground, I'll now share my screen and start with a brief presentation of what Webnozzles is actually about. So here we go. Okay, so yeah, I'm Norman. I already introduced myself. Scalable Minds is my company. We're primarily the developer of Webnozzles. Next to Webnozzles, we also build Voxelytics, which is an automated toolbox for automated processing of very large data sets with a focus on electron microscopy data, for doing everything from image preprocessing, including alignment, registration, and segmentation and of neurons, synapse detection, so that you finally can get connectomes or other artifacts that you might be interested in. So Webnozzles at its core is a visualization tool. It can stream data sets from a web server, and these data sets can be arbitrarily large. It's built for 3-dimensional data sets. It also works well for 2D data sets, and it can have multiple channels. And here you can see this full female adult fly brain that has been published a couple of years ago, and you can stream it very fast, even if you only have modest internet connections. So Webnozzles is not only a visualization tool, but it's also great for creating annotations. So this is me showing the brush features, what we call volume annotations. Yeah, it's great for basically creating segmentations manually that can either be used for analysis directly, and we'll have an example later on how you can do analysis with that, and then it's probably the more common case to use this as a ground truth for any machine learning type system. And we'll also have some examples how you can download this data and work with that in a Python environment. Webnozzles not only has volume annotation features, but also skeleton annotation features. The skeletons are great, especially for neurons and other tube-like features, because you can approximate them, and they're very cheap to obtain. So you can get create them very fast. Webnozzles also has a flight mode, which is an optimized mode for creating these skeletons. Technically speaking, the data here is projected onto the inside of a sphere, which makes it easy to rotate around. And this kind of resembles the egocentric perspective of a flight simulator. So that's why we called it the flight mode. Okay. And yeah, you can use it also for working with machine learning projects. We do that all the time, where we overlay different layers on top of the raw data. And here you can see a prediction that has been created by a machine learning system, and we can use the sliders here to find a good threshold. So the nuclei prediction, and then we can pick this threshold to turn this prediction into a segmentation then downstream. Webnozzles has a dedicated support for working with instant segmentations. Here you can see a feature what we call ID mapping, where you can create multiple mappings of where IDs are grouped together. So you can basically, they're equivalence classes. And you can switch between them very easily, and it makes it easy to debug your agglomeration pipeline if you have something like that. And it's something that's quite common in the field of connectomics to work with first an over segmentation and then agglomerate that. You can also do that manually, like you can create an ID mapping from inside of Webnozzles. There's this mode called the merger mode, where you can use these skeleton features to connect the segments of an open segmentation, and basically by that creating the ID mapping. Webnozzles can also be used for visualizing meshes, so you can generate meshes from an existing segmentation, either in the batch job that can run over a couple of hours depending on the size of your data set, or while brushing with the ad hoc mesh generation feature. It only works for smaller segments, but can basically work on the fly. And these meshes are great because you can look at them and you can get a feeling of how these segments look in 3D space, but you can also download them and then import them in Blender or another software to create visualizations for your publication or for a report or something like that. Everything Webnozzles has a link because it's a web-based tool, makes it very easy to collaborate with others in your group. So you can send a link to an annotation as we've seen here, and the zoom level and also the location is encoded into the URL. So your colleague will see the exact same screen that you're looking at. And this works for everything if you're just browsing around in a data set, or if you have created some annotations. And this can also, there can also be a token inside the link, which grants access to private data sets, because Webnozzles and dataset don't have to be public all the time, obviously. And if the token is then appended to the URL, then you can your colleague can also view that data. Or they can, of course, also you can invite them into your group, and if they are users in the same organization, then they might also be able to view that data. And because it's a web-based tool, it makes collaboration very easy. You can not only send around links, but you can also invite people into your group. Sorry, I just mentioned that. And it also has a task management system, so you can create tasks and they can be distributed among your user base. And you can have many users, like we have groups that have hundreds of annotators that work for them, and then they can create thousands or 10,000s of these tasks, and they will all be distributed among the annotator in a quite flexible manner, so that the workload is balanced among those people who actually have time to work on this. And then Webnozzles has features for monitoring the progress and also collecting all of the results afterwards. And if you don't have annotators yourself, we also have a paid service where you can create these tasks in Webnozzles, and then we can bring our annotators to help you with your annotation needs. So, and another feature I have been teasing in the talk on Friday as well is our support, and actually it's already in there in some limited capacity. So Webnozzles already has support for visualizing ZAR datasets, and it also exports all of the datasets in Webnozzles through the ZAR protocol, so that other tools are able to plug into that. And but not also all other tools, but also the Python library that I'll be showing in a second can use this as ZAR streaming to run analyses on top of that and work with the data. Okay, so I've seen that there have been a couple of questions in the chat, but it seems like Tom is working on that, so I'll just keep going. We are working on adding automated segmentation features to Webnozzles. The first one is a nuclei segmentation feature, and this is currently only available on webnozzles.org because we're still trying out how to deploy the infrastructure in an open source setting. But there you can try it out. You can upload a data set and click on process data set and start a nuclei and feral job from there. then will run on our server, and it will produce a result that looks something like this. And it's still a bit in a beta state, so where it works great for datasets that look very similar to the ones that we had in our training set. And we're trying to evolve these models as more and more people use this feature, so that we can improve the generalizability of this pre-trained model. And yeah, and we're trying to work on more and more of these features, so more and more segmentation models that can be incorporated into Webnozzles we're looking at. And if you have any specific ideas of what we should add, then please let me know. Right. So that's basically the short rundown of what Webnozzles can do at the moment. And the next big chapter, of course, is how to do workflow automation with the Python library. So there is this Python library. If you haven't seen it already, then you can check it out on GitHub. You can install it from your Python shell or in a Jupyter notebook, and I'll jump into the Jupyter notebook in a second. But before that, I also want to mention the documentation, which is on docs.webnozzles.org. And if you go there, you need to click on the tab Python library, and there you will see a bunch of examples and API reference, so you can read up what methods are available, what parameters these methods take, and we'll also have a guide in there. And yeah, that's the documentation. So today I want to focus on these 4 examples. And if you like, you can already open up this Jupyter notebook, which just has this bit.ly link right here. Sure, Tom will copy that in the chat in a second. And the 4 examples that we're going to look at is first the segmentation workflow. Then we're going to show you how to run a very simple analysis on a volume annotation that you can create manually in Webnozzles, and then run analysis in Python. And we're also going to look at data conversion, so how to convert data from Webnozzles to a TIFF stack and the other way around. And finally, we'll also look at how to create tasks and how to work with the annotations that have been created from that. All right, so are there any questions up until this point that haven't been written in the chat yet? Okay, then I'll jump over to...
I have one question.
Yeah.
So if I have a WKW dataset previously, can I easily convert it to a ZAR-based dataset, or do I need to create a new dataset or reuse the Webnozzles Cuber to create the dataset?
So you can use the WK Cuber to create ZAR datasets as well. And documentation on the Cuber is not perfect, as I'm sure you know, but there's a data format flag that you can put in there. So I think there's a section of how to do ZAR support. So it has this data format parameter that you can put into there, and you can put in ZAR, and you can even write these data sets to S3 or Google Cloud Storage, but also on disk. That also works.
Okay, thank you.
But if you have your data sets in WKW, then there's not necessarily a need to convert them to ZAR, because you can keep them in Webnozzles and stream them through Webnozzles as ZAR. But of course, if you want to use that in another tool, then you might want to convert that. There's also, you can also use the recubing to to recube that into ZAR. It can also do all of the Slurm parallelization that I'm sure you know about. Okay, is there another question? This was already pretty deep in the nitty-gritty section. So maybe we'll start a bit more on a higher level. So I have this Jupyter notebook. I'll increase the size a bit. And I've already run basically all of that, but I'll go through it now one by one, so that you can follow and show you what's going on. Okay, so first of all, what you need to do is install the Webnozzles package primarily, and for this Jupyter installation, we also need to install AIO HTTP, but that may not be necessary for when you run it on your own computer. And then we import the Webnozzles package as WK, which is just a shorthand for making it easier to write some code. So yeah, as I already ran that in this notebook, this was quite fast. So we're going to jump into the next section. So for interfacing with Webnozzles between the library, there's a token-based authentication. And if you have an account on webnozzles.org, then you can get your token with this link. If you don't want to click that link, you can also go to the sidebar right here, click on auth token, and then you'll be able to copy it around here. So this is just my token that I'm going to be using for demo purposes right now. And we're going to use this constant later on, so we're not going to use it right now, but later on. So we're going to start with this segmentation workflow, and we're first going to import a bunch of different modules. So some OS functionality is a bit of time for time measuring and naming things based on time. I'm going to import NumPy, which we're going to use for working with the numeric data. We're also going to import skimage, and in particular, we're going to use this trainable segmenter as a very simple segmentation model to run our data. And then we're also going to use matplotlib later on. So the workflow that I want to be showing today is we're going to start with an annotation that has already been created in Webnozzles. So this is a volume annotation from a sample data set that has been uploaded. It's a skin example from skimage. And already created an annotation here. This has 4 different classes, and we're going to use these voxels inside this bounding box that is defined here to create a segmentation model to then be able to run it on the full data set. And then we're going to upload that data set and visualize that in Webnozzles. So looking at the code again, we're first going to download this annotation. So this is a public annotation, so we can just paste in a link right here and download that. We're going to extract the bounding box from the annotation. And we're also going to open the data set. This is a new feature. You can now do open remote, which is a streaming-based access to data sets in Webnozzles. So you don't have to download the full thing, but you can download just individual bits as you're moving along. In this example, eventually we're going to download the whole thing. So you could also use the download functionality, but I'm going to use this open remote so that we don't need to download anything on disk, but keep everything in memory. And then this later part, we're going to extract a volume annotation data from the bounding box, and prepare also the raw data. So let's run this real quick. And as you can see, it's already done, so it's very quick. And what we now have is, so we have the annotation data that we created. And we prepared the data set to be able to read the raw microscopy data. So in the second step, we're going to initialize the machine learning model. This should run very quickly. So we're going to set up just a trainable segmenter class and give it some configuration. And this is basically taken straight out of the documentation of skimage. And here, what you would do in a real world scenario is basically set up your own machine learning based system. It could be a Keras or TensorFlow based system. Then step 3 is we're going to shuffle the data around a bit so that it works well with the segmenter that we have here. So we need to flip around the channels and yeah, squeeze the data. So this is just some boilerplate that we need to do for this particular segmenter. If you have a different setup, then here you would need to put in your own stuff. So let's start this, and this will run for about a minute on this machine. If you have a local system, that could be faster or slower depending on your hardware resources. But while this is running, we can already look at the fourth step, which is then starting a prediction. Again, we're gonna now what we're gonna do is we're gonna read the full thing, the full data. So this is the raw view, so it gives us a handle to the raw data that is streamed from the Webnozzles server, and we're just gonna call read without any arguments, which will give us the full thing. And this works well because the data set is not very large. If you have a large data set, then this would certainly crash with an out of memory exception, or you just terminate your process or something like that. So in a real world scenario, you would run this with a given offset and the size. So basically you define a bounding box on what you want to read here. So this will then be stored in main memory in this xPredict variable, and we're going to call the segmenter with that. And once that has been done, we get this variable y predicted. And with that, then we want to work on creating a new data set that we can upload to Webnozzles. So again, we need to do a bit of NumPy magic right here. So we need to extract we need to add this z dimension. I'm going to start this very quick because the other one is completed. And we're going to cast that into Uint8, so it can be used as a segmentation layer. Webnozzles also supports Uint16, 32, and 64, but 64 only works in some configurations. But because we only have 4 classes, 8-bit is completely sufficient. Okay, so this is also completed already. So the prediction is done. So we can now go to the 5th step, which is now creating a new Webnozzles data set. We're first going to create a temporary directory, which is some Python syntax for how you can do that. This with statement is quite handy because it will remove the temporary directory after the with statement is closed, so you don't have to worry about any data leakage. But now what's happening here, so we're going to create a new Webnozzles data set. Again, we're going to use this from the Webnozzles package we imported earlier. We're going to create a data set, going to write it to this temp directory on disk. We're going to pass in the voxel size, so that's the voxel size in nanometers. And we'll give it a name that we already created earlier on, and it's called skin segmented, and it has the current timestamp encoded into that. So a data set in Webnozzles consists of multiple layers. So next up, we're going to add a layer to this, and we're going to call that segmentation. Going to let Webnozzles know that this is a segmentation style layer. So layers can either be a segmentation or a color category, and color is basically everything from raw microscopy data to probability maps. And segmentation is reserved for instant segmentations, where semantic segmentations can also be represented as that. Then we're going to add the D type, so that's Uint8 if you remember correctly, and we're going to pass into compress that, and we're also going to pass in the larger segment ID, which will be handy or is required for Webnozzles to know, because then we'll use that for when you're brushing and you want to create a new segment, so it knows where to start to count. Okay, so now we have this segmentation layer. We're going to set the bounding box. And for that, we're just going to reuse the bounding box of the other layer, which is our color layer, which is the raw microscopy data. And in the Webnozzles data model, each of these layers can have mags, which is short for magnification, and it's basically the multi-resolution pyramid that you may be familiar with from other tools. And it starts at 1. So we're just going to add this mark, and we're going to write this segmentation right to it. So in this line, we actually have written now this prediction that has been created in the previous step on disk. And now it's available on disk. And now what we want to do is we want to upload all of that to Webnozzles. So we're going to upload this new data set that we have created here. It has a unique name with a date in it. And we're going to use a handy feature here, which is layers to link. And this allows you to link layers from another data set that is already present on Webnozzles. And to reuse a layer, right? And in this particular case, we don't want to upload the color layer again, which has the raw image data, but we just want to link that from this other data set. Yeah, so this will upload that, and it will return a uploaded data set object. And the last thing that's going to happen is that we're just going to print this, and then we can click on this. So let's run this. It will now basically create a temporary folder. It will add all of this data, write it out. It will upload this data set to Webnozzles, and once it's done, which is right now, we can open this and now look at this in Webnozzles. And I'm already logged in, so I can see this data right away, right? So yeah, and this basically is now this segmentation that we uploaded. And now we can share that to a colleague, send this link. We can, I was mentioning this token feature, so you can click this copy sharing link, and then this secure token will be baked into the URL, will be copied directly to your clipboard. So this would now be something that you can put in Slack or somewhere to send to your colleagues. So that you can look at this and maybe help you fix things, right? So maybe here would be something that we want to touch up, or down here also some issues. And it's not very surprising because this trainable segmenter from skimage is a very basic system, and yeah, but if you have a more sophisticated model, then you will get better results, right? And it's in this tutorial, I don't want to focus too much on the actual segmentation that is happening, but more on how you can interface with Webnozzles. So this basically concludes the first example of how you can run this automated segmentation as a workflow. Are there any questions? All right, then let's go on to the next example. In this example, I have already created a small volume annotation, and by the way, this is a feature that lets you jump to a specific location in the data, or to find some location where there actually is some segment. Okay, but yeah, in this example annotation, I have already been creating a very simple and small annotation. It only has these 2 segments. Also click here to jump to these 2 segments. And I want to show you this example where you can now download this annotation and basically count the voxels to derive the volume of this annotation that I did. And it's only a very small annotation, so I only do that in one section. So this is obviously a toy example, but can also work with larger annotations that you have created manually. So let's get started. First, I put in the annotation URL as a constant right here, and we're going to run wk annotation download with this URL. And this will download the full annotation I did. And because this is only a small annotation, it is very fast. And now next up, let's look at the code that can actually run this analysis. And this is quite specific to this volume analysis, but here you can plug in any kind of analysis that you may want to do with or run. Also call to a different tool if you would like. But what I want to show you is basically the specifics of the Webnozzles API and libraries, so that you know about them and you can work with that when writing your own scripts. Okay, so first we're going to create this empty dictionary where we're going to put in our data later on. It's going to be statistics per segment ID, and remember we have only 2, so this in the end will have 2 entries that we're going to print. So we're gonna take the annotation object that we have. We're gonna work with the volume layer of this annotation, and this function basically unpacks that into a temporary folder so that you can access that as a regular Webnozzles layer, just how we work with the other data in the previous example. So we're going to get a segmentation layer. And this is only available from within this with statement, so that's it will be cleaned up afterwards again. So now let's go through quickly line by line. And we're first going to look at what the voxel size is, and handily that is already stored within the annotation, so we can just access that. However, we're going to multiply that by the magnification, and it's a bit pointless for this particular example because we have this in Mach 1. So it will just be multiplied by 1. So effectively what we're going to get is we're going to get the size of each voxels in nanometers as a NumPy array, or as and which will be able then to multiply the number of voxels later on to get the volume. Now, the next thing that we're going to do is we're going to access the individual chunks of the of this segmentation, and so we're first we have this segmentation layer, and we're going to call get finest magnification as we did here, and finest will give you basically like the highest resolution that this layer has available. Also, this volume annotations that you're creating are in an image pyramid, so you can also access lower resolutions if you like, but now we're interested in actually the highest resolution so that we can get the most accurate volume readouts. And we're going to call this function get views on disk, and this will give us only the chunks of this entire data set that may have been annotated that are actually have some manual annotations in them. And if we don't do that, then we might get the full thing, and that wouldn't fit in RAM and would also be pointless because it might be sparse anyway, right? Because it will be quite hard for anybody to create a manual annotation of a very large data sets with the manual brush tools. So this is basically a performance optimization that might be necessary for this kind of tasks. And then what we're now going to do is we're going to iterate over these chunks, and we're just going to call read. And again, this will give us basically the full data of each of these chunks. And we're going to use the NumPy stack function to put them all together into one big NumPy array. And now
sorry,
we have.
Norman, can you quickly explain again what get views on disk means and how this chunks? So maybe this is too advanced. Sorry.
No, I mean, let's talk about that briefly. So Webnozzles internally stores the data sets in a chunked fashion. So it particularly, I think it always uses 32 by 32 by 32 sized chunks to represent the data internally. And this get views on this function will give you basically a handle for each of these chunks that actually have some data written to that. And because we are here working with a volume annotation, that means all of the chunks from potentially very large data sets that have had some brushing going on in them, right? So let's look at this example right here, right? So this data set is actually quite large. Can also, yeah, it has like 5,000 by almost 9,000 by 3,500 voxels. But the actual annotations that I did are only on a very small portion of the data, right? Because it only concerns basically this area over here. And now what this function will do is basically give us a handle of each of these chunks that are involved in this small area of the data where I actually did some brushing, right? So that we don't need to run the full thing, but only, or don't need to read in the full data set, but only the ones where actually some data has been written to. Yeah, is that clear? Does that answer your question?
Yeah, that answers my question. So basically it skips all 0 chunks from the data set.
Absolutely. Yeah, that's what it does. Okay, so now that we have the segmentation data, we're going to run this NumPy function called numpy.unique, and with the return counts argument, and that will give us two tuples or lists where we get the IDs of all of the segments that are in this annotation that we created, and the counts of the voxels. So like how many voxels have been labeled with the respective ID. And we're just going to iterate over that. We're going to zip both so that we can work them in tandem. We're going to skip this special ID 0, which is basically everything that hasn't been annotated, because we don't want to count the size of that. So we're just going to call continue here. Now we're going to calculate the voxel size in nanometer cubed by just multiplying the 3 components. And with that, we can compute the volume, right? So we're going to, again, we have already the count. This is the number of voxels per segment. I'm going to multiply that by this voxel size. And that's our volume that we get. And this we're going to append to our statistics object that we created earlier. And yeah, we're going to do that for all segments that we have. In this particular example, it's just 0 and then the 2 segments that we have actually annotated right here. So this ran very quickly. And down here now, let me run this real quick. Now we're just gonna iterate over this statistics object that we have, and we're gonna print it out. So here we have ID1, which has 11,000 voxels, and this volume in size, right? And the other one is this other size. All right, so this is a very simple example of how you can work with these volume annotations. I think the most important things that you should know about is that you can download these annotations. You can open up the volume annotation, volume layers as just segmentation layers that you can access. And then we talked a bit about this get views on disk optimization, so you don't have to work with the full data, and you can basically skip all of the empty chunks in the data set. All right. Are there any other questions for this use case or example? Exactly, yeah. So the empty chunks are not written, and they will be skipped here. Okay. Any other questions? No? Okay. So now the next example is actually I flipped the ordering here. Now I'm going to talk about task creation real quickly, about how you can create tasks from a Jupyter notebook, and how you can also then work with the results that have been provided. I already did a bit of preparation for this, and I can show you right now what I actually did. Let me just close these up right here. So I first created a task type which is kind of like a template for tasks in Webnozzles that includes a description of what you can do, or what the user should be able should do, right? So this is kind of, you can put in a tutorial here. Typically, we also include like a link to a video or something so that annotators know what they are supposed to do. And also has a name and a team that is attached to it, and it can have a bunch of more settings. Like you can configure what the users are supposed to have in terms of configuration. But I don't want to go too much in detail on this right now. You can find all of the details in the documentation and hit us up at another point if you have any questions about that. But I wanted to mention that I already have created that in the system here. I also created a project. A project is a grouping of multiple tasks, and they are basically the entity that are then can be visualized in a project progress dashboard. So you can know how many tasks of a specific project have already been done. And you can also assign a priority to that. So if you have multiple annotation projects running in parallel, then you can dynamically shift this priority. So when a user requests to get a new task, then the one with the highest priority will be picked first. So I also included that in my preparation. And then I also specified a data set, which is a fairly small data set, and we can have a look at that in a second, or maybe right now. This looks like, this is this data set, and it's a small cutout of the other layer 4 data set I was showing you earlier. And basically the task for the user will now be to brush this nuclei, right? So this one only has one, this small cutout only has this one nuclei. So we're only going to seed one location, but if you have a large data set with many nuclei and you already know where the locations are, then you could create multiple tasks. But for the sake of this example, we're just going to create one task. So, and the way to create this task is actually quite simple from the Python API. But there's this concept of the Webnozzles context that I want to explain real quickly, so that you know how that works. And so again, we have this with statement, which is only available in Python, and to work with something or to work with a resource that is specified here within this block that is opened up by this with statement. And in this case, we're creating this Webnozzles context, and we're supplying in our token. And if you remember earlier, the token is your authentication token. And this is required because to create a task, you need to be authenticated. And yeah, this basically provides the authentication transparently. And then we're going to create this task, and for that I want to show you how the documentation looks like, because here we can also look at all of the available arguments. And so we're going to run this create function. We're going to add in the task type ID. You remember I already created that and just showed that. Going to add the project name, the dataset name, then the needed experience domain and value. This is this is a key value pair that belongs to users, so you can add experiences to individual users so that they will only get assigned tasks where they actually qualified for. So in this particular example, I think I just called it very generic annotation, the domain, and the value is numeric and just be 1. So basically everybody who has these tags attached to them will be eligible to getting this task. And then the last required argument is the starting position. And this will be a location that we have predefined and we're going to pass in. And then there are a bunch of other arguments that you can pass in, like a starting rotation, which is only makes sense for the flight mode. Tasks can also be spawned with multiple instances if you want to create redundancy, right? So you can have multiple instances of the very same task, and Webnozzles will make sure that they will be distributed to multiple different people so that you get good redundancy and you can run some consensus after that. And you can also append a script ID to that. So there's a Webnozzles front-end script that you can attach. And the last argument that you can supply is a bounding box. So you can restrict the work of a user to a given bounding box. If you leave that out, then the whole data set will be visible to them. Yeah, but in this particular example, we'll just stick with the required arguments. So I have the task type, ID, the project name, the data set, this experience domain and value, and a starting position. And here I'm supplying that as a vector3 int. So this is a data type that ships with the Webnozzles package, and to specify this location. And I actually got this location from Webnozzles, so I just moved around here and I copied this over and pasted that in there. So that's how I created that. But if you have an automated system and you, for example, have like a nuclei detection system, so you know the rough positions, but you want to get better annotations from your users, then you could obviously seed this automatically, and you can create as many tasks as you want in a for loop or something like that. So yeah, now what I'm going to do is I'm going to create this task, and this has been successful. So get this HTTP 200 status. But more importantly, I'll get some information about the task that has been created. So there's somewhere back here is probably the task ID. Not seeing it right now. Oh, here it is. Yeah. So, and this will then be I can use this for further references later on. So now let's go to my user view. I'm going to go to the dashboard and the tasks section, and then now I can get new task. This is what one of your users or you yourself could be doing. And now I got one of these tasks, and yeah, it's actually the one I just created. And I'm going to open this. And right here, now I'm at this location that I find, and now I can use the brush feature and basically trace around this nuclei, and I haven't been doing perfectly great here. Okay, so let's just so yeah, now I can basically do annotation work, but I don't want to bore you too much with that. So I'm just gonna click finish and go to dashboard. So this task is now gone. And because now what we want to do is we want to access this annotation that I've just created. So again, we're going to authenticate with our Webnozzles context. Now we're going to access the projects. So remember, projects are groupings of multiple tasks, and we associated the task that we created earlier on by this name. So we're going to get this project right now as an object. Then we're going to use that to access the tasks. And then we're going to iterate over all those tasks that are available. And we're going to get the annotation info, which is a list, because remember that tasks can have multiple instances. So each of these annotation info will correspond to an instance that has already been worked on. Or in particular, we're actually filtering out here the annotation infos that actually are finished, right? So this annotation state finished, and because I just clicked on the finish button, that is actually this task has been finished. And then we're going to print that. And now we should get two examples right here. And we're just going to get one. Okay, that's a bit weird. Oh no, here's the second one, right? So the first one was something that I did yesterday, so don't worry about that. But the other one is actually the task we just worked on. And yeah, and now I have access to the annotation. I can even download the annotation, which is printed over here. So I have access to the skeleton, which is non-existent, but I also can work with this in the same way as the previous example where we did volume analysis and do any calculations with this annotation. So this is just an annotation object that I can use in any kind of way, right? So I could, for example, I could merge all of these from the multiple tasks into one data set, or I could use them directly for running in feeding them into a machine learning system as training data, or basically do whatever you want from the Python land here. So that's one way of accessing these tasks. And you can also get them through the ID or something like that. But I think actually accessing them through a project is a preferred way for working with a group of tasks. Right. So yeah, are there any questions about the task system in Webnozzles and how to work with that with the Python library? Okay, cool. So then next up is the last example, and it's actually about importing and exporting data. And so as a twofold, the first, we're going to export a data set as a TIFF sequence. And then the second one, we're going to convert a TIFF sequence into the wkw format, which you can then use to upload to Webnozzles, for example. Please note that exporting a data set is also available from the UI. So if you go here, you can create a bounding box of your data and then click this export button right here, and it will you can select which layer you want to download, and then it will prepare that in a background job. And once that is done, then you can download a zip file of all of the TIFF files. And also uploading works also from the UI, so you don't need to go to, you can just go here to add data set and drop in your TIFF sequence right here, and Webnozzles will then convert that for you once you uploaded that. But just to show you how that works internally and how you could do that if you want to work, if you basically want to skip the UI and work with that from Python. I'm going to show you how to do that real quick. So first, we're going to import this TIFF file library and also pathlib path to work with some paths. So this TIFF file we're going to use to write out the TIFF files, and this we're going to use to to create some folders. So yeah, what we're going to do here is we're going to open this data set, and again we're going to use this dataset.openRemote function, which doesn't download the data set, but it just gives you a handle to the data set. And we're going to use this L4 sample. This is again the one that I just showed you. So it's a fairly small cutout. I think it's 1024 sized cube. So it's the raw data should be around a gigabyte to download, and it's public data set, so we don't need to worry about authentication here. So we're first going to open this data set, then we're going to get the color layer, and from that we're going to get the Mach 1, which is the highest resolution magnification that you can get here. So next up, we're going to specify this folder where we want to write the TIFF files to as a path, and then we're actually going to create that. And if it already exists, that's fine, but I don't think it does at the moment. And now there's actually an optimization in the Webnozzles package for writing out or for reading sections from this volumetric data. It's called the get buffered slice reader, and it has an optimization because the data in Webnozzles is chunked. So all of the chunks are 32 by 32 by 32, and reading one section at a time basically requires you to read all these 32, or requires you to read in 32 sections at once. And if you would do that one section after another, basically you would read in these chunks yeah, in worst case scenario, 33 times, but it's always the same data, so it's pointless to download that all over again. So what this does is basically when you access that, or when you spawn that, it will provide an iterator that downloads all of the required chunks once, but it will give you the slice data in one section after another, and it will internally make sure to buffer that data correctly, so you don't have to worry about that. And you can use that again with a with statement, where you call this get buffered slice reader on the magnification. Going to get this reader object from that, and this is an iterator. So we're gonna iterate over that. We're also going to enumerate that so that we get a numbering basically of the sections, right? So, and we're only going to need this numbering so that we can create a file name for that. Yeah, and here what we're doing is, so we're going to write this data out to this TIFF folder that we've created, and we're going to create, yeah, they're just going to be numbered, right? And this syntax is for zero padding that, right? So we always going to have 5 digits. That's the 5. We're going to pad it with 0, and D is for decimal, I guess. It's a bit of a weird syntax, but this expression basically creates this 0 padded file names. And we're going to pass in the slice data, and then, yeah, that's it. So we're going to write that out, and we're going to run that right now. So this is going to take a minute or so, but I think we'll be able to follow along. Maybe if scalable actually lets me see some data between. Oh yeah, here it is. So now the first TIFF files are written. You go right. So this interface is batched, so it will only update every now and then. And maybe while this is running, oops, come on. Let me just download that and show that it actually looks like the data that we have been seeing on Webnozzles. So just to convince you that it actually works. And okay, maybe while this is running, are there any questions about how this downloading works? Okay, now it's complete. And so let's just see if the numbers add up. And okay, it only shows me up till 1,000, but it should be 1,024 sections. There. Okay, now I have this. I downloaded the full data set. The data set is fairly small. So again, this is a bit of a toy example, but you can also use this get buffered slice reader for just a bounding box of data that you want to use, or yeah, work with it in any kind of way you want. Okay, now here's just another example of how you can also add that. If you don't want to use this buffered slice reader, you can also call read directly on the mag object, and you can give it an absolute offset, which in this case is just actually the top left of the bounding box, so the starting location, which is, I think in the case of this data set is not at 0, 0, right? So it's actually, the whole data set has an offset to it. So that's why I didn't put it in there. And then we're just going to read this size. So essentially the first section. And now we have that here as a NumPy array. We're going to reshape that for matplotlib, and I'm going to use this. And so this is another way of how you can access that, but please again, be careful with using that, because in the background, actually, because Webnozzles uses this chunked data storage, actually 32 sections need to be downloaded in order to fulfill this read requests. Okay, and then I can visualize that right here. So this also works.
Is there a way to get the number of chunks, or do you just calculate them by the size here? So if I load a data set, it's possible that, for example, if I'm unlucky that I just capture a corner of the data set, is there a way to make sure that this don't happen, or that I then get the full chunks and don't read parts of it?
I'm not sure I fully understand that. So, I mean, what I can tell you is that if whatever offset you put in here will be the thing that gets read, but if you're unlucky and if you put in a location that doesn't have any data to that, then you will get no data. Is that what you meant, or?
And no, my question was more in the direction on how to optimize this read command, but.
Okay, yeah. I mean, that there are actually quite some optimizations. I don't really have a good example here right now, but I can show you something in the documentation that we use internally quite a lot, and that's, for example, it's this for each chunk function, which is quite handy. So you can give it a so first of all, you can from your Mac, you can call this getView function, and you can provide a bounding box to it, basically, right? So you can give it an offset and a size, and then we'll be restricted to this thing. Now you have a view object, and on this view object you can call for each chunk, and for this you can give it a function, and this will then be called for each chunk that is available, right? And the library itself will make sure that it picks a reasonable size chunk. So I think in general it will get like gigabytes chunks, like 1024 cubes or something like that. You can also set it explicitly if you want what the chunk size will be, and this can then also run on multiprocessing or even on Slurm or something like that. So you can pass around this this function, and this is probably a good way to work with chunked aligned data. Yeah.
Okay, thank you. That helped indeed a lot.
Yeah, and and then there's a couple more functions like that, right? I mean, I also already told you about this buffered slice reader and writer, or just the reader, but there's also a writer. And then there's also zip chunks, which is quite handy if you have two layers, for example, and you want to have them in tandem. They could even be of different, you can have different resolutions, and then it will the function will calculate a good chunk size.
Can they be from different data sets?
I don't think it, I'm not 100% sure if it works for multiple data sets. It could actually work for that, and I think that then we'll just take the intersection of the bounding box of the data sets.
Okay.
Yeah, but I'm not 100% sure if it works for multiple data sets. Yeah. So yeah, so I think maybe we can just have a look at these functions, and they're used under the hood quite a lot. Like, for example, for downsampling is implemented with this function. There's also a copy dataset function that uses this for each chunk, so that you can, if you copy a dataset from one location to the next, then it will use this function internally, which allows it to be run on either a multiprocessing executor, so in parallel on a single machine, but it could also be run on a Slurm cluster or something like that. So for parallelization. Okay. Cool. Okay. And any other questions about how to export data? Work with that? And I think that the point why I included this is also because now this is like a TIFF sequence, and you can now use that in any kind of tool also that you want, right? So you can open this up in Fiji or something else and work from there, right? Okay, and then the last example for now is how to run the inverse operation of this. So how to create a TIFF sequence, no, a Webnozzles dataset from a TIFF sequence. And for that, I don't want to show you how to do that with a Python library itself, but with this command line tool called the Webnozzles Cuber. It actually needs to be installed separately, but it's also available on pip like this. And yeah, and the way how you call it is Python-m, which stands for module, then wk-cuber. Then you give it a scale, which is the voxel size in nanometers again, because that's not encoded into this TIFF files that we just created. We're also going to supply the max magnification that we want, because this tool will automatically create a resolution pyramid for you. And then we're going to give it the input folder and the output folder where the data set is supposed to be. And yeah, and we're just going to run that on the command line. And after that, we're going to open this data set up with the Python library again. So let's run that. This, by the way, can run in, so can be parallelized internally, and it will do that automatically, right? So here you can see it's already using a pool of 2 workers to do that. And yeah, this has this fancy Python progress bars to show some progress. Unfortunately, compressing is done in 1 step for this size of data set because it's fairly small. So we have to wait a bit. Yeah, and this cuber also is capable of outputting it this not only as a Webnozzles wrap format, so this is the Webnozzles native format, but if you pass it -- data format ZAR, then you will get a ZAR dataset that could even be directly written to S3 or Google Cloud storage or something like that. And then you from there you can also then import that into Webnozzles without needing to upload it again, right? So that would be quite handy probably. Okay, so what actually the tool is doing, so it's first converting these all of these images, right? So it found our 1024 files that we created. First, it writes that into Webnozzles wrap files without compression. And it does that because then it can parallelize things in the initial run better. But then it compresses that. This doesn't help too much for raw microscopy data because it's a lossless compression format. LZ4 is used internally, but it definitely makes a big difference for any segmentation data that you may have. And even for raw data, it might save a few bytes here and there. And so it did the compression, and then after that, it also does some downsampling. So it creates a Mach 2 to 1, which means that only X and Y are actually downsampled. And that is because this data set is an isotropic, and it wants to find basically good approximation so that in each Mach, the voxels are the most square they can be, basically. So, and because we restricted it to a max magnification of 4, it first creates Mach 2 to 1 and then 4, 4, 2, and then it stops right there. And now we can look at also what this hierarchy looks like, right? So this is what a WKW dataset looks like. This is a folder with a JSON file, and then another folder for each of the layers. We only have one right here, and then a nested folder hierarchy for each of the magnifications. And then inside there are then the actual data that just are these WKW formats. And right here, if we would create a ZAR dataset, then this part would be like the ZAR arrays. All right, and yeah, and now we just open that so we can access that. Maybe let me just add something here, dataset and layers, to print that out. And here you can see we have this color layer that we can also see in the folder structure. So no surprises here. All right.
One question.
Yeah.
If I have created a SAR data set with another tool or just by a plain Python library, can I just recreate this folder structure and Webnozzles will detect it, or do I need special things so that it works?
No, I think that should actually work. So you need to supply, you need to create this data source properties JSON basically. And there you can even specify a path for each of the magnifications where it can find the ZAR array. So you may not even need to move around the data, but you need to create this data source properties JSON for now and put that into the binary data folder that you have access to. And then the next couple of weeks, we're also going to add UI features so that you can actually import that directly from the UI, but that's not there yet, right? So we're working on the technical foundations at the moment, and we're going to add more and more expose the ZAR functionality to the UI more and more in the coming weeks and months.
Okay, so the Webnozzles Cuba convert ZAR became obsolete by this new version, right?
Yeah, basically, yeah. No, I think it's fair to say. That being said, I mean, Webnozzles doesn't support all of the available compressors yet, and it may be reasonable to rechunk the data that you may already have. So maybe it still has some reason for existence. Okay, are there any other questions about how to create a Webnozzles data set from a TIFF sequence, or you can also use it from other file formats? That I would also just briefly mention.
Questions in the chat by John. So what is that JSON? Is it very complex and similar to .zar attributes maybe?
Yeah, and that's a good question. So it's a proprietary format that we have at the moment. It's not very complex. So let me just show you an example very quick. Yes. So this is what it looks like. Has the name of the data set, the scale, just the voxel size in nanometers, and then the layers, and then one JSON object per layer with a bunch of fields in there, the bounding box notably. And then all of the max or resolutions are listed in here. So, and that's basically it. So it's just metadata to find or to know up without traversing the file system what is there. And it's very similar to what we're also working on with OMI and GFF and the Z-adders format. So again, we are kind of building this as we speak, and in the next couple of months, we'll also be just going to be able to read OMI and GFF metadata file and use that from Webnozzles. So hopefully this proprietary format will become obsolete soon. Okay. Cool. Any other questions? Okay, so if there are not any questions, then I'm just going to show this last slide one more time. Thanks everybody for joining this workshop today. If you do have any questions later on, feel free to send me an email or contact me on Twitter, or on also write on image.sc. We're also, Webnozzles is also available on there, and we try to answer very quickly. If you haven't, please try out Webnozzles on webnozzles.org. And if you want to stay in touch on any updates on what we're building, then please follow us on Twitter. That's actually the best channel to learn about anything new about the tool. And also, as we're developing the ZAR features more and more, we'll also have more and more updates on the Twitter channel there. And of course, you already joined the workshop today, so there's no need to do that. All right, so thanks, everybody. I'll stop the screen share right now. Have a good day.